So yeah, let's briefly talk about reasoning about configurable system performance through the lens of causality. Actually, like performance reasoning and trying to figure out, the performance of the system is a very interesting topic to me. I had a paper on performance of state machine replication protocols, dissecting the what's it called? It doesn't matter. Anyway, it just figuring out the performance of systems it can be pretty challenging, right? Even when we talk about simpler systems, like I looked at the performance of state machine replication protocols that are just like exist by themselves, in a vacuum, right? Don't interact with pretty much anything else. They just run the state machine replication. There is a log, there is some like state machine, the key value database, and that's it. But real systems are way more complicated, right? Real systems have multiple components, multiple systems interacting with each other. So how do we even try to figure out the performance of these systems? Can we estimate the performance of systems in different conditions, in different environments? Can we figure out what configurations, what settings impact the performance and by how much? So, and this is what this paper is trying to solve, at least in the context of, these configurable systems that are not distributed, right? So they mostly focus on the systems that run on a single machine, but these systems are comprised of multiple components that interact with each other, right? So each component, each module will have its own configuration. Obviously there is hardware configuration, the platform you're running this particular system on, and all of this impact the performance. So the authors say that a lot of past work on trying to reason about the performance and predict the performance, as you change the configurations and settings, it has been done pretty much following the trying to find correlations between the settings and the performance, right? So maybe if you change a particular number, the performance is going to change in some way. So if you can find those correlations, if you can mine those correlations or learn those correlations with, a variety of AI and machine learning techniques or statistical methods, whatever, then, you can say, okay, this setting correlates with the performance in a certain way, and that's kind of good enough, right? But what the authors of this paper say is pretty much that correlation is not the causality, right? Just because things correlate a certain way, that doesn't mean that one causes another. Actually, you don't even know the direction, but not even the direction of causality. Like there can be something else that causes both of those things that you observe the correlation of. And they have a few examples where they observe some correlation, but it turns out to be really not the causality, right? And these traditional performance systems, they tend to fail. So what the authors are doing here, they're saying that, okay, let's find the causal model, right? Which is essentially a directed acyclic graph of all those different things, and they can cause each other, right? So you tend to start with your settings, your configurations, right? Like here, they have an example. Your configuration, maybe like a bit rate, buffer size, batch size. This is for the deep stream system that I believe processes some media information, some video and whatnot. And then you have your metrics that you want to measure, like throughputs, frames per second, or energy used. And you have like a bunch of things that sit in between that you can potentially measure, like number of cache misses or branch misses and so on. And they try to figure out what causes what, right? So if they can figure out the causality, and not only the causality, but if they can also figure out those functions, right? Like changes of one parameter, not only increases, let's say, branch misses, but how it increases, then you can talk about predicting the performance with different parameters that you haven't observed empirically. And in this example, obviously, they have only like 4 different software options, but in reality, the software is very complicated. There's hundreds, if not thousands, of options. So trying all possible options and all possible permutations, it's just not feasible. So having a model that comes up with this causal relations and comes up with these functions that allow you to describe how one impacts another can be very useful. I'm not really going to talk too much about how they achieve this. Maybe I should a little bit, but essentially, yeah, they represent this as a graph, right? So you can start with the graph of all, like everything you have, all the options, all the intermediate mechanisms that you can observe and not your objectives, and then you can they do a few sample runs with different configurations, and they start to calculate these causal relations. They start with this like fully connected graph, I think, and then they start to prune the connections and figure out the directions of these connections over a few iterations. I believe the protocol, the algorithm that they use is not something that they specifically came up. They're using the fast causal inference algorithm, which I believe they took from a textbook. So, I suspect that maybe this is not a super novel part, but applied to systems, I guess it's cool. Yeah, this essentially allows them to figure out to the best of their abilities, right? It's not a perfect system. Figure out the causal relations, not just correlations, but the causality of one configuration on something else that they can observe, and finally on the final metrics that they target and they want to optimize. So yeah, that's pretty much it. I think the high level overview is causality is important when you try to figure out why things don't work, right? Why is the big question. So it's not just about the correlation. And they show that they can use this algorithm in a system to figure out the causality between all of these configuration parameters and some things they can observe intermediately, and the final metrics, and predict things. And what's important is they were able to predict the performance of systems going from like one hardware configuration to another, like to completely unknown environments. They claim that because they know this causality, they can still predict the performance as you go forward. And another important aspect, I think, in their case study, they show that the tool that they have developed can actually illustrate, because it can find those causal relationships between all of these parameters and metrics and everything. They can debug systems, and they can do so very quickly. They claim that they can do so much quicker than human engineers without any proper tools. And they also compare it with other tools and show that their system works better as well. So yeah, this is where I kind of want to stop. Super high level overview.